So in this video, we talk about the I/O architecture. So we define the input-output as a subsystem of components that move coded data between external devices and a host system. Basically, the I/O subsystem includes a block of main memory that are devoted to the I/O functions, buses that move data into and out a system, control modules in the host and the peripheral devices, interface to external components such as keyboard or disks, and also the cabling or communication link between the host system and its peripherals. So here the general architecture of the I/O system. We can see that the CPU connect to the main memory, and then from main memory we have the I/O buses right here. From the bus we can have the different I/O module. For example, this module gonna connect to a printer. This I/O module have the devices interface, and that connect to the disk. And also we have another I/O module that have the different devices connect to the monitor or keyboard system. So that's gonna be a basically this is a device adapter circuit board or adapter cardboard have the some plug in the motherboard. So here the total motherboard, and here the OCAP interface where we can plug the cable to connect with the I/O devices. In general, the I/O can be controlled in 5 general ways. The first one we call a program I/O reserve a register for each of I/O device. Each register is continually polled to detect the data arrival. The second one, that's interrupt-driven I/O, allow the CPU to do other things until the I/O is requested. The third one, that's a memory map I/Os. So basically this one share memory address space between the I/O devices and the program memory. The next one, that the directed memory access DMA. So basically this scheme upload the I/O processing to a special purpose chip that takes care of the detail, okay? And the CPU does not have to process, but the designated chip gonna take care of I/O processing. And the last one, that's the general I/O. So that's basically this scheme is the dedicated I/O processor. Okay. So this is an idealized I/O subsystem that you interrupt. So basically each device connect to its interrupt line and to the interrupt controller. So the controller signal the CPU when any of the interrupt line are asserted. We have the CPU right here. We have the interrupt control right here. So basically all the I/O device or subsystem gonna connect to this controller. So we have the keyboard, we have the mouse, we have the printer, we have the disk right here. So wherever the controller have the detect any of the interrupt signal asserted, it's gonna inform the CPU, and then we're gonna do some processing in order to allow the connection with the communication with the I/O subsystem. So a system that you interrupt, and standard of the interrupt signal is checked at the top of the fetch, decode, and execute cycle. A particular code that is executed whenever an interrupt occurs, and that's going to be determined by a set of addresses called interrupt vector, and that's stored in the low memory. So basically a system state is safe before the interrupt service routine is executed and is restored afterward. So here the flow chart of the interrupt processing. So basically you have to start right here, and when the system detect the interrupt signal, it's gonna save all the variable and the register of the system at the current point, and then just look up at the ISR address in the interrupt vector table, and then once it's find the ISR, it's gonna place the ISR address into the PC. That's the program counter, and also branch to the ISR. Okay, so once branches gonna start the task request by the interrupt. So it's basically perform the work specified by the interrupt, and once the return gonna come back to the point where the information gonna store right here. The basically that retrieve the register and the variable before it start the work by the interrupt, and then go run to the top of the fetch, decode, and execute cycle. So that's the basic of the flow chart of the interrupt. So in the memory map IO device, basically the devices and the memory share the same address space. So each of IO device has its own reserved block of memory, and the memory map IO therefore looks just like a memory access from the point of view of the CPU, and thus the same instruction move data and to and forth from the IO and the memory, and that's significantly simplify the system design actually. So in a small system, the low-level detail of the data transfer upload to the I/O controller and just build into the I/O devices, and that's not gonna be significantly reduce the task of the main CPU. So here the direct memory access configuration, we can see that actually the DMA and the CPU share a bus. And the basically the DMA run at the higher priority and still the memory cycle of the still cycle of the CPU. This is because of this is because of the timing parameter of the I/O devices. So basically, the I/O device, if it detect no activity within a specified period, they gonna time out and abort the I/O process. So to avoid the device timeout, the DMA use the memory cycle that could otherwise be used by the CPU, and that's what we call a cycle steering. Okay, so basically that's a cycle steering to prevent the timeout of the communication. So in very large system employ actually the channel I/O. So the channel I/O basically consists of one or more I/O processor that control various channel path, and that's basically slow devices so that the terminal or printer are combined into a single faster channel. And for example, on the IBM mainframe, multiplexed channel are called a multiplexor channel, and a faster one are called a selector channel. The channel I/O is distinguished from the DMA by the intelligence of the IOP. So the IOP basically negotiate the protocol, issue device command, translate the storage coding to the memory coding, and can transfer the entire file group of the file independent of the host CPU. And the host had only to create the program instruction for the I/O operation and tell the IOP where to find them. Here the configuration and diagram of the channel I/O. You can see that the main memory and CPU right here have the memory bus, and that connect to the I/O bridge, and from there we have the I/O bus that gonna have the multiple I/O processor for different devices. For example, I/O processor for the terminal control for printer, I/O processor for disk, for tape, and I/O processor for the printer. Another one right here, actually. Um, so you can see that there's a specific I/O processor, IOP processor for different I/O devices. So the character I/O devices process 1 byte or a character at a time. Um, example include the modems, keyboard, or mice, and also keyboards are usually connected through the interrupt-driven I/O system. And on the other hand, the block I/O devices handle a byte group. So most of mass storage devices, as a disk or tape, have block I/O devices, and block I/O systems are most efficiently connected through the DMA or channel I/O. On the other hand, the I/O buses, unlike memory buses, operate asynchronously. So basically, this request for bus access must be arbitrated among the devices involved. And the bus control line basically activate the devices when they are needed, raise the signal when the error and has occurred, and it's also possible reset the device when necessary. There's a number of data line is the width of the number of data line is represent the width of the bus. So a bus clock coordinate activity and provide bit cell boundary for the communication between different component with the main system. So here's a graphical representation of the generic DMA configuration. You can see that the DMA circuit connects to a data bus, and with the control and address bus as well, and from there gonna connect to different devices interface, and that's gonna connect to different I/O devices. Okay. So that's basically some of the basic information of the I/O subsystem, and we also can read more detailed information in the textbook. The next lecture we're gonna discuss about the different data transmission mode and also different type of a storage system.